we go.
All right. Well, it is my pleasure to introduce my good friend and sometime collaborator, Armin, and he's currently at Space Telescope, and but previously did his PhD at the University of Washington, spent some time in Chile and at Harvard, and has worked on high-redshift supernovae. And we were on competing teams then. And then, but he has also worked on the light echoes from supernovae, and of course stuff related to HST and JWST. So I'm excited to hear about all the new stuff they got going on. So welcome.
Thank you. Well, thanks for having me here. It's always a pleasure to come to Santa Barbara. So last time I was here, that was February 2020. That was my last trip for a while during the time.
You did a public talk.
Actually, yes, I gave a public talk at that time. Yes, lots has changed since then. Yeah, it's amazing how much has changed. I mean, I actually got married, good time, and I met my wife in January 2020 in Chile. So yeah, talking about COVID throwing things into your path. Anyway. So it's really a pleasure to be here, and finally we are really back to normal. And since the last time I was here, actually my focus of my science has changed a little bit. I'm a one of the NIRCam scientists at Space Telescope, and of course JWST has been launched, and it really has been an absolutely amazing time to use this new telescope and the new data. And so I will tell you today a little bit about the high-C transient universe that we have discovered with JWST. Of course, a lot of people have worked on that, and I really want to point out the people in the trenches. These are postdocs at STSAI, and also Christopher Kersey. She's a grad student at the University of Arizona. And beside them, there are also a lot of other people that have contributed. I also want to point out Ori, Lou, and Eiji. So we have kind of like led this team. So let me just go into it. So this is just a quick outline. I will give you a little bit of background. I think the vast majority of you know already about supernova, but I want to put them in context of the high-C universe, in particular the paired stability supernova. And in part 2, I will show you a little bit how we discovered the transients in JWST data in the JADES and Cosmos surveys. And then I will show you in part 3, NIRCam and NIRSpec follow-up of this high redshift supernova. So just like very quickly, I think you also know that, why are supernova important? They're important end stages of stellar evolution. They produce and distribute all of these heavy elements that we are made of in the rich interstellar material. Of course, there are standard candles. This type 1a dark energy was discovered. And there are also excellent probes of high energy physics and explosion mechanisms. I mean, the most energetic explosions are supernova and other transients. And one other important thing is they trace the star formation rate in that the core collapse supernova, in some way we can just assume they're instantaneous, and the number of core collapse supernova then traces the star formation rate. Also, just very quickly, from progenitors to supernova, just like the basics, we start with a hydrogen core, and we have hydrogen to helium fusion in the core. And so that energy production, that pressure counteracts the gravity, and that's the reason we have this equilibrium and stable stars. At some point, hydrogen runs out. It's all converted to helium in the core. And then you start to burn helium in the core, and you have shell burning of hydrogen. So if the star is less massive than 7 solar masses, after the helium is burned to carbon and oxygen, there's not enough gravity there to increase to a temperature and pressure that can burn carbon and oxygen. And so you are left over with a planetary nebula, and then later on with just the carbon-oxygen core, which we call white dwarf. And that would just like float in the universe without doing anything. And only if there's a companion that pushes this white dwarf over the Chandrasekhar limit, about 1.4 solar masses, then gravity wins against the electron degeneracy, and you have this thermonuclear explosion. So this is like the one path for the low mass stars, like our sun. Then on the other side, you have the massive stars. And there, after you burn hydrogen and helium, you have continued burning to the next elements all the way up to iron. Sometimes you have this shell model, you have all of these shells burning, and that sometimes leads to this eruption like for FRK. But sooner or later, you have an iron core and you lose the support and it collapses either into a neutron star or a black hole. So this is an overview slide that was inspired by a slide I saw given by Avishai Galyam. And so you have here progenitors, then what kind of supernova type they normally produce, and what the mass range is. This mass range is just approximate. You know, a lot of other things come in that can shift this up and down. But so in general, as I said, you have for smaller than 7 solar masses, you have carbon oxygen white dwarf that may cause a type 1a supernova. If it's a little bit more massive, so 7 to 11 solar masses, and you have a red supergiant, it's still a little bit, so we definitely have type 2Ps, the most common supernova that we have. But there is also some evidence that you can have an electron capture supernova where electrons are captured, I think by neon, could be wrong. And so when you take away these electrons, the electron degeneracy cannot support it anymore. It triggers an explosion and you have an electron capture supernova. The most famous example that is thought to be an electron capture supernova is a Crab nebula. There's a lot of evidence that this is one local one. There are also a few examples of electron capture supernova in the low C universe, but you know, I would say they are consistent, but it's not for sure yet that there's that these are indeed electron capture supernova. So that's actually one of the more interesting supernova that we still.
Hey, that's our work, so you should be sure about it.
Yeah, you can tell me more about it later, you know.
Give a seminar.
So you also have, you know, type supernova 87A, like supernova that come from blue supergiants. And then, of course, you have the stripped envelope supernova that come from Wolf-Rayet stars. These are stars that most likely have lost the envelopes through binary interaction, if they're binaries, or some of these stars are also expected to lose some of the envelopes. I think I don't have to go into this. We base our classification of supernova purely on observations, and it basically depends on if they have hydrogen. If yes, it's a type 2. And if it doesn't have hydrogen, then but helium, it's a 1b. If it has no helium, it's a 1c. And then, of course, you also have the 1a's. So, you know, it's just a purely observational one. And it actually turns out that 1b, c's, and type 2s are one physical mechanism, and type 1a is a different physical mechanism. So besides these, we can also look at some more exotic supernova and events. And these are in general coming from more massive progenitors from 30 all the way up to 130 solar masses and more. So ones that we know are, for example, broadline 1Cs that are associated with gamma ray bursts. And then, of course, you have things like FRK that have circumstellar material from previous eruptions. And then you have the supernova running into this circumstellar material, producing supernova type 2Ns. And then you have the ones that are most likely from really massive ones, and they are the one that we are most interested in is a pair instability supernova, and we'll talk about that a little bit more. These are thought to come from really massive stars. And yeah, one last thing, of course, the lower mass ones will produce neutron stars, and the higher mass ones black holes. So, pair instability supernova, what are these? In a pair instability supernova, you have gamma rays that then decay into a positron-electron pair. So it's pair production. So you have this massive star supported by these gamma rays, by this pressure, and then you convert it into electrons and positrons. And if this is supported and is a runaway effect, you basically lose the pressure support, and then you have it will ignite a supernova. So in order to produce this positron-electron pair, you have to have a high enough temperature that the light particles have energies bigger than the sum of these two, electron positrons. So that's the reason you need really high temperature. You only have that in the course of the very high mass stars, and you only have that for low metallicity, because in low metallicity you have inefficient cooling, which leads to high stellar mass. And the only way you have this low metallicity is either you go back in time to the early universe, to high redshift, or you have these dinky dwarf galaxies that didn't have much star formation, and therefore not much metallicity. So there are a couple of examples of these low Z pair-instability supernova candidates, and the first one is 07Bi. That was gallium in 2009. So if you look down here at the light curve is not great, but you can see that it's very long, so it's a very long event. And if you look at the spectra and you do some modeling, you also find that it is consistent with a pair instability supernova, with some of these pair instability supernova models. The progenitor is thought to be about 100 solar mass with a nickel mass of 3, which is definitely much higher than you normally have with, for example, type 1As. At the late phases, you still have an agreement between some of these pair instability models and the nebular phase spectra. So this is a pretty good candidate for pair instability supernova. Yes.
I don't think so, because we found later a clone sort of 07Bi, one that looks spectroscopically similar, and light curve similar. The only reason we think that people thought that this one could be pair instability is because, there's not pre-max data, but you need a very long rise, like 100-day rise basically. In the one that is sort of a twin of this, we do have the rise, and it doesn't have that short rise. So
it has a short rise.
Yes, it has a shorter rise. It doesn't have that long of a rise. So I suspect that this is, if we had more data, this would not fit.
It is a candidate. I mean, I'm not saying it is one, but it's the data for this one is consistent with the pair instability supernova. But I agree, if you have a twin that has a very short, which one is that? What's the number?
I had to go back and look. I'm too old and I forgot.
So what are the features in the spectrum that indicate a pair instability supernova? Or is it just the persistence?
It's, I'm not a spectroscopist, I'm more an imaging light curve person, but I think it is actually very difficult to have a smoking gun feature for a pair instability supernova. It has features similar than some of the other core collapse supernova. And so that's actually one of the big issues. How do you say this for sure? And as Andy said, the long rise time is normally an indication for a pair instability supernova, because 1BCs and 1As, type 2s, they in general have a much shorter rise time than more 20 days, maybe 30 days, and not like 80 days or more, or 100 days that we expect for pair instability supernova. But yeah, I don't know which features these are. I mean, Andy actually probably knows more about spectroscopy than I, but I cannot identify them by just like that.
Yeah, you should produce a lot of oxygen, and anyway, it's complicated. Move on for now.
So here's another one that is a very good candidate, and I think I didn't show the image of 07Bi, but the host also was one of these little dwarf galaxies. Here for this one, 18 IBB, you can see to the lower left that the to the left is a supernova and to the right is a template. You can see this little blue dot here is a host. It's a very faint dwarf galaxy. And so just from the host, this is definitely consistent with what we expect a low-Z host should look like. And then here you can look at the light curve. You see that the rise time is also relatively long. You know, of course, we don't have very early data, but just like this amount is already longer than the vast majority of supernova, and it also lasts very long. You know, typical time scale of a type 1a or type 2, I think the longest are type 2Ps, which are about 100 to 200 days with a plateau. And all the other supernova are in general shorter, with the exception of superluminous supernova, most likely parent-stability supernova and TDEs. So one of the issues with this supernova is that there is evidence of circumstellar material interaction. And that, of course, makes things very difficult because the circumstellar material interaction can also cause that the supernova light curve lasts much longer, has a much longer time scale. So Steve Schulze is the author of this, and it's a very long paper with a lot of details. I also would say this supernova is consistent with the parent stability, but I wouldn't say there is a smoking gun evidence that it is. And one of the main reasons is that because of the circumstellar material interaction. Here, the numbers that you get when you fit the light curves and do also fitting, the progenitor is bigger than 130 solar masses and the nickel mass more than 25 solar masses. That, of course, assumes it is a parent stability supernova. So take that definitely with a big grain of salt. Yep.
I'm not a supernova person. Why do we care about the mass of nickel?
I think the mass of nickel. Why do we care of the mass of nickel? I think the mass of the nickel for type 1As, for example, tells us what the initial mass was. You know, so normally there's a correlation between the initial total mass with the nickel mass.
Well, it's just one of the easiest things to measure. If that's the power source of a supernova, then you can measure just the peak of the light curve, the width of the light curve, figure out the amount of nickel that it would take to power that.
Yes.
So then if you know that, then it tells you, okay, that's a massive star. I mean, to have 25 solar masses of nickel means you had to have an initial progenitor that was huge.
So most progenitors derive from nickel.
More kind of, but it's also the broadness of the light curve. It takes just a lot of time for the energy to diffuse out of a bigger star. And so the broader your light curve, the bigger the star. Those are very approximate numbers. But the other thing is a parent stability supernova is actually a thermonuclear supernova. And so that, even though it's almost acts like a core collapse, like it's a massive star, so you would think it'd be core collapse, but it becomes thermonuclear. So that creates nickel. And but that nickel is an assumption that that's the power source. If the power source is interaction with circumstellar material, that assumption is wrong and everything is wrong.
Yes.
So
the circumstellar interaction, you know, as Andy said, it really makes life difficult.
Okay.
Because besides superluminous supernova, these type 2Ns are also some type of superluminous supernova because you can have this really bright supernova, much brighter than typical core collapse supernova, because all of this kinetic energy of the supernova, when it's interacting with the circumstellar material, gets converted into light. And so you have this extra power source that is a kinetic energy that normally you don't have like that in a normal supernova that doesn't interact.
that was on this paper, so you could believe this one. Not the previous one I wasn't. So, you know.
Make a little asterisk.
Yeah.
The other way around.
Yeah.
Open the door, lower the temperature here a little bit.
But anyhow, I always give each other shit, you know. Here's another really interesting result. And so Xing et al., they took spectra of a star in our galaxy. I think it was a halo, but I'm not 100% sure. And they look for the elemental abundances. And so they found that in this star, if they compared to models, it's a very low Z star, they find that the elemental abundances are best explained with a parent stability supernova it's this model down here. And so especially the sodium abundance here is very low and is in disagreement with the normal supernova abundances. So the idea is here that you have the first supernova in a galaxy happen, for example, Perseid supernova most likely, it enriches the interstellar material, and so the next star that forms will have the elemental abundance of a parent-stability supernova, because all of these initial higher order elements are produced by stars and distributed by the supernova. So the very first star should have the imprint of the first supernova. So this is definitely far out of my field. I did think it looked very convincing. I talked a little bit with someone who knows a little bit more about the stuff, and they say that, you know, the error bars that they have here are sometimes underestimated. And so when you have an upper limit like that, they said like, well, it probably is not completely inconsistent with some of these other ones. But, you know, I mean, if I look at this, I do have to say that the parent-stability model does look much better, much more consistent than any of the other ones. So I thought it was really cool, you know. And so now switch gears very quickly and just like look at the high redshift universe. So with HST over the last 20 years, we have pushed the high redshift universe to about Z of 10. And now with JWST, we go to 14. The best candidates are now redshift 14.2 or something like that. I mean, it's really amazing. We really go to within the first billion year of the age of the universe. And one of the first results was that they did find more high redshift galaxies than they expected. And there are two possible explanations. You can have a higher star formation rate, or you can have a top-heavy stellar initial mass function. And this is where supernova come in. When you define kappa as a volumetric quark-like supernova rate divided by the cosmic star formation rate density, because quark-like supernova traces stellar population evolution, a constant kappa would mean a constant IMF. If you have a changing kappa, that means you have a changing IMF, for example, a top-heavy IMF. And that basically goes back. Oh, so this is a plot from Lou Strolger that we have that he has made for one of our proposals. So here on the y-axis, you can see the core collapse supernova rate. So from redshift of 0 to 0.8, it is pretty well known. We have all of these ground-based surveys that go to about that redshift range, and we can calculate the core collapse supernova rate. However, then when you go to higher redshift, redshift of 1 to 2, all of these data points, these huge error bars, are coming just from a few supernovae. For example, this highest redshift ones, Lou said, comes from one supernovae. So then when you look, what are different kappas mean? So the current best fit is this green line. And you can believe that or not, because it's heavily influenced from this few poorly measured data point at high redshift. The evolving kappa is orange, and a constant kappa is purple. So this evolving kappa is just one example. But you can see that the differences really come in at high redshift. So if we can get good measurements, even from 1 to 2, but hopefully all the way to redshift 5, we can really constrain that and figure out what's how the IMF has changed.
You should define IMF for not.
Oh, I'm sorry. Yes. The IMF is the initial mass function of stars. And so it basically is the number density of each mass bin. Like, what's the relative number of stars for a given mass range. And top heavy means that you have more high massive stars than in the current universe. And that is not something unlikely because, as I said before, if you have low metallicity, you can build more massive stars. And so I would say it is kind of like an expectation that we have a top-heavy IMF in the high redshift universe. And this is what we can do with supernova. We can first count all of the core collapse supernova as the first test and say like, hey, how many core collapse supernova do we have? What's the supernova rate? And then if we have enough supernova, we can even look at the different types of supernova that gives us indication about the different mass ranges. So, you know, if you find pan-stability supernova, then of course we know there are really massive stars that we don't have now. If we find 1C, the broad line 1Cs, and I will talk about this a little bit later, that means we actually have a good number of these 30 to 50 solar mass stars. And 1C, broad line 1Cs, I think are only a few percent of the total number of supernovas, a relative fraction. So, what can we do with JWST? The big issue is that JWST has a very small field of view, and it's not nimble. What I mean is not nimble. You don't slew fast, you have a lot of overhead, so it's very hard to have a big survey. So you have this big trade-off between depth, number of filters, and area. And you need all three to really find supernova at high redshift. And so on the right side, you see basically the depth of a survey versus its survey area. And you know, you can see you have these really deep surveys that go to 30th magnitude. This is JADES and NG deep. And then, but they're relatively small. And then you have things like Cosmos Web that has, you know, is much, much bigger, but only has 4 filters and only goes to 28. So that's kind of like the trade-off that we have. And the hope is that with JWST, we can get supernova out to, you know, C equals 10 to 15 at some point. So part of our discoveries with JADES and Cosmos. So first, the JADES survey, that was our first survey we did. And Krista, from a grad student from University of Arizona, was leading the discovery part with our group at SDSCI. So the initial epochs of JADES were these two. There was one epoch in 2022 and another epoch in 2023. There were like some stragglers on November 15th that they couldn't do previously. There was like some issues with guiding. But if you look at epoch 2 and then epoch 4 and 5, this was mainly DD time. So between October 2nd and November 28th, we got the data, we reduced it, did the difference imaging, found the supernova, got all of the photos, vetted them, wrote the DD proposal, it got accepted, scheduled, and the images were taken, and spectra all within 2 months. It was really crazy. I mean, it was like amazing that we actually could turn it around. And the key actually is that the window for the observations does close. You know, so the problem with JWST is if you're not in the continuum viewing zones, which are in the north and in the south, JWST can only observe a certain part of sky for a certain time. And so when you get the data, that's probably one of the 1 or 2 or 3 windows where you can observe it. So if you don't turn it around quickly and get the observations, then you probably miss it until the next observation windows, which can be, you know, a few months to half a year later. So as you can see in the plot, this is kind of like the coverage of the different epochs. It's a real mess. It's amazing. So typically we have 3 to 4 epochs, but like 7 or 8 filters per supernova. And we found 45 transient in 2002 and 35 in 2003. And here's a really nice example of a galaxy at redshift 1. I mean, first of all, for redshift 1 galaxies, if you see this in ground-based, it's a little speck. And now you see here, this is like a well-resolved galaxy. The bottom is a difference image. And so you can see that 2 supernova one that happened in 2002 and the other one that happened in 2003. And if you look at the image here, so this is a one that you could identify by eye, but then this one here, you can barely see because it's buried in the galaxy. So, you know, difference imaging is really essential to find the supernova. And this one is a relative close one, about 28.7 magnitudes, or 28.5, I would say, on average. And then here is one of our high redshift candidates. You can see the host galaxy has a high, has a 4.5 photo Z. And if you look at the supernova itself, you can also see how it is very red. So it basically only pops up in 356 and also in 444. And in the bluer bands, in the short, the near infrared, you don't see much. And that's also indicate that it's actually indeed a very high redshift supernova. So just a couple of words about Cosmos. Cosmos Web is one of the biggest surveys, but they only took the data in one epoch until now. However, there's another project, it's called Primer, and that one overlaps with Cosmos and was taken at a different epoch. And this overlap is 5 times the area of JWST, but it only goes to 28th magnitude, not to 30th. So this is an example of we're going significantly wider, but not as deep. In this one difference image for this one epoch, we did find about 70 to 80 supernova, and we also were successful with our DD follow-up. And so now imagine you have this big area. I think it was about 150 arc-minute square. And we found 3 high redshift supernova in this region. And we were really lucky because we could put near spec, which is like a really small field of view. And we could put 3 of these supernova into near spec. And then the near cam observations are here, we also covered. I mean, it was really amazing. And actually, that's what I want to really emphasize. When you have these surveys and you don't have much telescope time, having a big survey and then triggering the follow-up, you can actually save a lot of time by doing this targeted deeper fields. So part 3 is the last part. I want to show you some of the observations, some of the supernova that we have discovered. So the first one is led by Matt Siebert. It's 23 Atta, and we think it's a 1C BL, a broad line 1C, that are normally associated with gamma ray bursts, and it's at a redshift of C equals 2.83. I just want to emphasize this one more time. With JWST, in 20 years, we got like maybe 2 dozens of supernova between redshift 1 and 2. And the highest spectra was a 1.8 type 1A. And if I would show the spectra, it would look really crappy, you know. So now we are suddenly at a redshift of 2 to 3 or even more. It is really amazing. So here's the 2 epochs and the difference images. And so the art is you want to align the spectra near spec that you can get all 3 objects in these little slitlets. As you can see here, the supernova is actually this little dots down here. And we just barely could fit it in. These are just the trade-offs that you have to make so that you can get all 3 supernova into your spectroscopy masks. So the nice thing was actually, one second, we'll go back. You can also see that the supernova is here, and then we get a good chunk of the galaxy without the supernova down here in this spectra. And that's actually really important. So here you see in the upper panel, you see the traces. The uppermost trace is supernova, and then the lower trace is the host galaxy. So you can do a little bit of the game that you get the host galaxy spectrum from the lower slit, normalize it to fit the other spectra that contains a supernova and subtract it. And that subtracted spectrum is down here. That's imperfect because, of course, supernova spectra are not exact, or like spectra of galaxies depend also on positions. So you have some uncertainty there, some systematic there. But if you look at the lower spectra, you can see that there are some of these, broad wiggles that are that the supernova have. So here's a look at the light curve. And you can see it is actually a very nice light curve. We have a pretty good photometry. It was a bright one, relatively bright one. It was discovered at rise. That was actually the one supernova we predicted that it will rise and we will get a good spectra, and we were true, and it was true. So from the left to the right, you see the best fit 1BC, type 2, and 1A. And if you look at the bluest bands, you can see that type 1As do not fit the blue bands. Type 2s also have issues of fitting the blue band, but then for type 1BCs, you can see that this the fit is actually pretty good for a supernovae. When you look at the spectra and you look at the calcium line, and you look here on the left, on the right, you see different fits of different models of 1BCs, actually 1Cs that are broad line. And you can see that the calcium-rich ones up here do fit best. That's all relative. I mean, of course, this is not the best spectra that you can get. It's not as good as a high-quality spectra from low Z, but I would say it's consistent. It's not inconsistent with a 1C broad line. However, if you put all of these things together, the light curve fit of a 1BC is very good. It's the best from all of them. And the spectra also seems to be consistent with a 1C broad line. I think we can say that this is indeed a 1C broad line. And when you look at the light curve, you can see that it falls right in the middle of the delta M15 and the peak magnitude. So everything is definitely very consistent with a 1C broad line. And we do think that this is indeed a 1C broad line. So host galaxy metallicity is also consistent with this type of supernova, but low for other types of core collapse supernovae. So that was our first object. And now we have our second one, which is a likely supernova type 1A at a redshift of 2.9. And so you can see here on the left are the slits. It's barely in. It is, the redshift was correct. It is exactly what we expected, so that was good news. And if you look at the spectra and you overplot different types, so you have type 2s from the top, 1CBL, I think the next one is a 1B, and then you have a calcium-rich 1A and a type 1A to the bottom in the blue, in the light blue. It's tough to say, Nominally, the best fit is a calcium-rich type 1A. Also, if you look at some of these main lines here, you can see that the type 1As are a better fit. But I would say it's consistent. There's a hint that it's a type 1A, but I don't think I would be convinced yet. So if you look at the light curve, type 1A to the left, the other types to the right, you can see that the type 1A agrees very well. It's a pretty good fit. Where the other ones, the other types in different colors here are not that great. But again, I mean, you say like, yeah, if I squint and I don't want to find a type 1A, I could also say it's still consistent with some of the other supernovae. And so if you just look at the light curve and the spectroscopy and just look at the chi-square, a type 1A has the best fit from all of these. However, are you convinced? I mean, I wouldn't be quite convinced. And so we were thinking about what can we do to figure this out. And here comes this plot, and that's a little bit of a complicated plot, but as soon as you understand it, it's actually really nice. So Each of these panel are different color plots. And in each of these color plots, you see the trace of a supernova light curve of the different types. So on the left, you have type 1a, and then you have 1b's, 1c's, and type 2p's. And so you have three color plots. These trace of the supernova that we observe at low redshift, the color indicates the different phases, and the phases are shown here with early phases around peak, and then the blue ones, and then you go to green all the way to red. The data points are also showing the color of the phases. And as you can see, for type 1As, it actually works out really nicely. The phases of the different colors also agree with the phases of the models. For the other ones, for the other types, it's just not quite the same. And I think this plot, when you really think about it, really puts all of this together, the evolution and the color from the different bands. It says like, okay, it has to be consistent, not only for a given filter, but also for the color. So I think this is a very good type 1A candidate. And now to Cosmos. In Cosmos, we also have a type 1A supernova, this time at redshift of 2.2. And now you can see, I mean, this is an absolutely fantastic fit of the model in red to the observational data in black. So this is without a doubt a type 1A supernova. Justin is working on that. And so if you put both of these supernova on the Hubble diagram, you can see the typical type 1A supernova in black, basically going to a redshift, most of them redshift 0.8 from ground-based. And then you have a few of Hubble. You have some photometric ones, and then you have some lens supernova, also from HST and JWST very recently. And then they have this two supernova from our sample. And you can see with JWST, with more data, we will be able to really fill up this Hubble diagram here. So one of the keys is that dark energy, the impact of dark energy, you can see mainly between redshift 0 and 1. And at higher redshift, dark energy doesn't play a role. So why is it useful? Because we know what to expect. We should be able to fit the type 1As at higher redshift, and there shouldn't be any real fitting. It should just follow the relation that we get from a lower redshift. Any systematics, evolution, dust, you name it, any differences at the high redshift will indicate that there are some systematics that we don't understand. So I think at the high redshift type 1A are really important to pin down what we will do, what we're doing right now and will do with Roman, that we can say like, okay, we really understand type 1A supernova. We don't have any of the systematics and we understand what we're doing. So the last one I want to talk about is a high redshift one that is likely a core collapse supernova at redshift of 3.6. Dave Coulter is leading that. So you can see here the spectra, and it doesn't seem like we have much supernova light in this spectra, but the redshift was confirmed. So you can see the host galaxy fit here. It fits pretty well. If you get more data and get another spectra at that position without the supernova, then we might be able to tease something out. But if you look at the supernova and do a light curve fit, so here are the different bands, and you can see the red models, type 2s, fit this supernova best. And if you look at the host galaxy, the metallicity versus mass, you can also see that it's at the very low end of this host galaxies that we have for type 2s. So Dave is working on this right now. Hopefully we'll get it out in the next couple of weeks. He has a first draft ready to be reviewed. So we are going now up to redshifts of 3.6 this one says 2.9. It's actually 3.6. I should have changed that, you know. Oops. So, very quickly about the future. There is Cosmos 3D. That's another Cycle 3 program that will re-image Cosmos Web. However, in filters that we haven't observed until now, but one F115. So we have to think how we make use of that. Probably want to add some filters. So that's a really good program in 2025. There's also another program that just got approved, Nexus, that also goes very deep on the North Ecliptic Pole. So we can use that one to discover supernova. And then, of course, there's this STCI DD initiative that where the director asked for input from us at STCI and then from the community to suggest what we can do with DD time to look for long-term variability. And a big component, the report was submitted. I was a member of that committee, and it has a very strong high-Z component, about 300 hours on Cosmos, also the North Ecliptic Pole, and also clusters and follow-up. So this will now be implemented. The team still has to be formed at STCI, but hopefully in the next few months, there will be a good progress there. And then, of course, we have Roman, which has a very strong transient component of a deep field, about 10 square degrees. And it also has the wide area survey, about 1700 square degrees. We put in submitted a paper where we argue strongly that we can use this wide area survey that doesn't have a time component to just shuffle around these observations so that we can actually make a time domain survey, a rolling survey. So here's a different colors indicate different filters, and you can see when you arrange them in a better way, you actually can get about 20 epochs over 150 or 200 days, and that would be excellent for high redshift transients. And I just put up my conclusions, and I will stop here. Thank you. Questions?
You say in the JADE survey, 60 supernovae and 80 or so with Cosmos. Do you think these will be sufficient numbers that what you presented here were highlights, right? Individual targets and the features of them and how they were interesting. And it seems like where you want to go eventually is to be able to do some statistics.
Yes.
To try and determine evolution of perhaps the types or
yes
through redshift. Is that
that's correct? Yes.
Do you expect that this will be sufficient numbers to do those sorts of statistics? And do you think you'll be able to push based on what you've seen so far beyond these redshifts? I mean, 2 to 3 and 3+ is great. Do you think you'll be able to go even deeper, even higher Z?
Yes, I think so. I think what we did in the last year, you know, it was a proof of concept. We got the data, and I mean, I can promise you it was not easy to use all of this data, even though we had some of the scripts already ready, go through, find all the candidates. Now we have, for example, we have 76 hours of JWST time to follow up type 1As, like Justin Birel, he got a program approved for Cycle 3. So we can already now we have now the follow-up time approved for 10 type 1A supernovae. And if we multiplex, we probably can increase that number to 15 or 20. And so that's already a very good first step to increase these numbers that we have. The Nexus, the other program that got accepted, also has some follow-up component. And I really think that the DD initiative, putting in even more time in it, we will be at a point where we can really start to follow up these things on a bigger scale. For example, JADES goes down to 30th magnitude. If you have everything lined up and you can go to the detection limit, we will be able to get to higher redshifts. We have one supernova that is most likely at redshift 5.5. We don't have a spectra, unfortunately. but everything looks like, and it looks like one of these exotic, very luminous objects that by chance we have a lot of observations, and just from the light curve, it's actually clear it has to be really high redshift. So I think with the next round, we will go to redshift 5, 6, 7 with like the most extreme examples, and we can get a good sample that is relatively, for which we know the efficiency between redshift 1 and 3. So yes, it will take work, but I think because we had to apply for DD time every time we found something, which delays by like 2 months, this now everything's set up to follow them up fast. I think we will actually be able to really fill this up. Yes, but that's the ultimate goal with Roman as well, you know, in a few years when Roman comes online.
So I don't know that much about supernova, but type 1As are -19, right?
Yes.
How bright do some of these, in absolute magnitude, how bright do some of the superluminous ones?
So superluminous one are typically -22, like the typical superluminous one. Parent stability supernova, they're models.
Mhm.
They're thought to be bright. They're thought to be really long, which is good and bad. I think it's actually good because with a redshift time dilation as well, if you find them, you actually have time to observe them. You know, they should be there in 1 year, maybe even in 2 years for redshift bigger than 6. And they're supposed to be bright as well. So are they really this bright? We will hopefully know in the future. If they're not that bright, we might only be getting them up to redshift of 5 or 6. If they're really bright, with the deep surveys and maybe with Roman, we should get them to even higher redshift range. But yes, so they are thought to be, we all hope that they are brighter than -19.
I'm super sorry if I missed this, but like finding these supernova and getting this great data up to redshift 3.6 is just the most insane thing I've ever heard.
Mhm.
I'm curious as to how you are actually identifying the candidates for follow-up. Like I don't know a survey that goes that deep.
Yes, so
Are they all serendipitous?
I unfortunately kicked out this plot, I think. I can show you later on. So there's a plot. When you look at the color magnitude diagrams and you pin it by redshift and you put in your models, each supernova type occupies certain reaches of the color magnitude diagram.
I had one of the plots like that.
Did I have one?
Yeah. It's like that. I think Quimby made the plot or something.
Yeah. Oh, here it is. Yes. And this is how you identify them. So I went over that too quickly, I guess. You know, I'm sorry. Orange here are superluminous supernova. So you can see they're relatively bright. The perceptibility supernova are in red. And that's over different phases and stuff like that, you know. The type 1As are light blue, and the type 2s are this purplish here. As you can see, this is redshift 1 to 2, 2 to 3, 3 to 4, and 4 to 5. So this one here is actually our best perceptibility supernova candidate because it's too blue for type 1As and type 2s. It is actually at a redshift of 3.5, and that's here is redshift bin of 3 to 4. So if you make this just like 3.5 or more, the blue even goes further to the right. So this one looks definitely like a core collapse supernova or perceptibility supernova. We still have to, you know, dig deep in there. That's from the Cosmos field, our next set of papers. But this is how we do it. The X's are Cosmos and the crosses are Jades. So you can see how Jades, because it goes so much deeper, here in this one redshift bin, you mainly have Jades, and just these two are from Cosmos.
Mhm.
And the same here. You only have basically Jades, you have this one here from Cosmos, and then these two from Cosmos. And that's kind of like the game, you know. So When you go wide and not as deep, you will mainly find redshift 1 to 2, maybe some 2 to 3, but then these really bright ones, principality, superluminous supernova, TDEs and stuff like that might pop in, and you might find them. Yes. So that assumes that you have good photosees. So everything hinges on that. For Cosmos and Jades, it was no problem because they are so well-known fields, and you have the whole big Cosmos group and Jades group. The only purpose from them that are doing is getting photosees of high redshift galaxies that they can do their science. So when you find a transient field, you just like send an email to, Hollis the Machine Akins, that's the name that we gave him, because, we're asking for photosees. 1 hour later, here's your photosee. And it has been so accurate, So what you really need is the machinery that if I give you 500 candidates of transients, you can give me a really good photosee estimate of the galaxies in that area. And then you can start to figure out which ones you want to follow up. And it has worked out really well until now. Yeah, very good question. Yeah. Any other questions?
I have 3, but
Yeah.
it can wait after.
Okay,
All right, well, why don't we thank Armin again?
thank you.
And we'll be taking Armin to lunch at noon. If you haven't signed up, please do.
It's really going on.
Where do you want to chat?
Okay,
Okay.
and ask